Hello everyone and welcome back in this series about multivariate calculus. Today we're going to look at some of the important theorems of multivariate calculus. So, since we already defined the different types of integrals, we can start by stating the first theorem, the fundamental theorem for line integrals. So, we let C be a smooth curve given by the vector function r, where t is in between a and b, and then let f be a differentiable function of 2 or 3 variables whose gradient vector del of f is continuous on the curve. Then we have that the line integral on the curve C of the gradient of f is equal to dr is equal to f evaluated at r of b minus f evaluated r of a. And here we can have a drawing where the point A and the point B are the points of R evaluated A or R evaluated B. Now we're going to look at the significance of this theorem. So this theorem says that we can evaluate the line integral of a conservative vector field simply by knowing the value of f at the endpoints of the curve. Well, here we know that the conservative vector field is a vector field such that it can be written, so f can be written as the gradient of a function, and this means that the field is conservative. This theorem we saw before can look familiar in the way that we already saw a similar version on single variate calculus. If we recall the fundamental theorem of calculus, where we have the integral from a to b of derivative of f dx being equal to f evaluated b minus f evaluated at a, we said this is the one-dimensional version of the previous theorem. Now we can look at an example of an application of this fundamental theorem. So we want to find the work done by the gravitational field. We already know that the gravitational field is given by this formula here. And we want to find the work done in a moving particle with mass m from the point 3, 4, 12 to the point 2, 2, 0. So we know that F is a conservative vector field because we know that the gravitational field acts in this way. In fact, then we write that f is equal to the gradient of a function, where this little function is equal to this formula. Of course, we already are given this formula, or we can compute it, but then we can apply the fundamental theorem of line integrals. So the work done on the particle is the line integral on the curve C of f, that is equal of the line integral, of course, on the gradient of little f, since we saw before that big F is conservative. And what we obtain by applying the formula we had before is f evaluated at 2, 2, 9 minus f evaluated at 3, 4, 12. Actually, this should be 0, as the point here is 0. And this gives us mg that multiplies 1 over 2 square root 2 minus 1 over 13. The next theorem we're going to analyze is about independence of path. We say that the line integral on curve C of f, the vector field, is independent of path in D if and only if this line integral along the curve C is equal to 0 for every closed path C in D. Then, if f is a conservative vector field, that means that there exists a potential function. The next theorem we are going to analyze is related to independence of path. We have that the line integral along the curve C of the vector field f is independent of path in D if and only if this line integral is equal to 0 for every closed path C in D. Furthermore, then we have that f is a conservative vector field. So there exists a potential function f such that the gradient of f is equal to our vector field big F. Since we know that the line integral of any conservative vector field f is independent of path, then we have that the line integral is equal to 0 for any closed path. The physical interpretation is that the work done, since we know that the work is a line integral of a vector field by a conservative force field, as it moves an object around a closed path, is 0. An example of this can be when an object is moved along a closed path in a gravitational field that we know being conservative. Next theorem is Green's theorem. So we can just state it. If we have a C being positively oriented, piecewise smooth, simple closed curve in the plane. So an example of this is here we have a drawing, and the curves, the green ones on the borders are here example of curves that satisfy the conditions for this theorem, not those ones though. So if we have this curve C that satisfies this condition, and D being the region bounded by C, then if P and Q have continuous partial derivatives, P and Q being part of the function that we want to integrate. So if this P and Q have continuous partial derivatives on an open region that contains D, then this line integral, so the line integral of P dx plus Q dy is equal, on the line integral on C, is equal to the double integral on the domain D of the partial derivative respect to x of Q minus the partial derivative respect to y of P dA. This theorem can be useful, but we can generalize it further for more cases, but it's still a good theorem to have. We generalize now Green's theorem from 2 dimensions to 3 dimensions with Stokes' theorem. So let S be an oriented surface bounded by a curve C with positive orientation. Then let F be a vector field whose components are class C1. C1 means that the components are continuous and also the first derivative is continuous. Then the line integral along the curve C of F is equal to the double integral on the surface S of the curl of F. We can write this saying that the boundary curve of F C is written as partial of S, and the theorem then will be expressed in this way, but the only thing that's changed is that this C is now referred to as partial of S. The significance of this theorem is that the line integral around the boundary curve S of S, so the line integral around this curve of the tangential component of F, so as I saw before, this is equal to the surface integral over S of the normal component of the curl of F, since the other side is a double integral of the curl of F dot ds. So, yeah. To understand and to see also why this theorem is true, we have this exercise where we have to verify Stokes' theorem for a function, actually for a surface, and a vector field F in 3 dimensions. In this example, so we start by computing the first side of the equation of the theorem and seeing that is equal to the other side. So we compute first the double integral along the surface, and then we compute the line integral about the boundary curve. So we denote S to be the upper hemisphere and partial of S being the boundary curve. Then we can note that in this case, since our vector field is defined as x plus y plus z, which is this vector field here in the image, we can note that the curl of f is 0. We can note this as in like in any point there is no rotation occurring. The divergence is positive at any point here, but the curl is 0. So we can write that the right hand side of the formula that we saw before in the theorem is 0. Then we aim to compute the line integral. So first we note that at any point in the boundary curve partial of S, that is this one highlighted in the figure, the tangent to this curve is the vector minus y x 0. That is the vector that goes in this way. Actually. Then we have that this vector is always perpendicular to the vector field that we saw before. The vector field we saw before is this one. We see that any vector that is tangent to the curve, to the boundary curve, is perpendicular to the vector field. This means that the dot product between f and ds here along the curve partial of s will always give 0. In this way, we verified Stokes' theorem because we found out that both sides of the equation, the equation of the theorem, are 0. The theorem was exactly this one. Now we're going to state another theorem, the divergence theorem, for which we let E being a simple solid region and S being the boundary surface of E. Then we give E with positive orientation. If we let F to be a vector field with components of class C1, then the double integral on the surface S of the vector field is equal to the triple integral on the volume E of the divergence of F. What does this mean? The significance of this theorem is that under given conditions, which are the positive orientation and the component functions to be of class C1, we have that the flux of F, of the vector field across the boundary surface of E, is equal to the triple integral of the divergence of F over E. This theorem means that we can know something about what happens in the volume E just by knowing some information about what happens in the surface. For this reason, this theorem is used often also in electricity and magnetism, for example, where to calculate the electric field generated by a set of charged particles, for example, we use this theorem knowing some conditions from which then we derive the formulas for the electric field. In general, all of these theorems are useful and will come handy in many different scenarios. So, for now, this is all. In the next video, we will see some definitions and some application or examples about tensor calculus. For now, it's all. See you in the next video.